上的转。然后如果要上下调整，这边把这个锁给解除了，然后这边这个球就可以随意转了，转好了再把这个锁给扭上，调个合适的角度。完了这需要调下球，要调整，然后需要往上一点，用这个球。然后它如果要黑板就往左转，如果它挂了，那就拔掉线重插，像上次介绍的这样。观察一下那个，这边有了 ，perfect。然后观察它如果挂了就拔进重插，之后就调整一下，之后比如说人一来了就不要两个人。然后下节课的照相会。好好讲。这个角度不错，以后掌控的人就坐这儿。然后这边电脑，你要干什么？听课吗？
对，它因为就是短时间的最简单的。好像是。但我知道 direct 它也是做方式的，那个方式里的它FTA 我之前做那个他学的有次我上课他就把看不懂，然后我就去简单版的换了。对，东西有点难，很难的。我是吗？他老有写 PDF 给出来，
completely different. All she's like, oh, well, such a good, like if you think this is on your weeks or something, that's not it.
就是因为就是方式为了
I used to.
就完全
Now it's like, by
Okay, good afternoon everyone. So Fefe is out of town and I will be taking these classes. So we'll be talking about relational algebra and SQL. So today we'll mostly talk about relational algebra, and if I could cover some parts of the SQL, it would be good. And so Fefe has talked about till selection operator in the relational algebra, and also he has talked about, I think, projection. So we'll start with union and set difference. But before that, we had so has Fefe talked about some closure properties of relational algebra? Closure property?
Yeah.
So it's like that you have both the operators like selection and projection. So the instance, so you have to have a relational instance that goes into this selection or the projection operator and it outputs another relational instance. So it's same as like the real numbers. So you apply some positive, negative, means addition, subtraction, multiplication, division, these operators in the real number domains and you get a real number. So in the same way, we get relational instance for the input for selection and the output is relational instance. So that is exactly the closure property in case of relational algebra. So we deal with relational instance instead of real numbers in the arithmetic domain. Now let's talk about for something like this projection and the selection operator, we can interchange them actually. So if we apply, say this is name and ratings on S2, and after that we do the selection of ratings greater than 8. That is also possible. So what makes this possible is that the outcome is always same. So there is many ways to get to the final result, the final relational instance. But the thing is over here is that relational algebra is procedural or operational. So relational algebra is procedural and operational, but the tuple calculus that Fefe might cover in the next lecture is actually declarative. So I will tell about what is declarative and what is procedural operations. Just take one example. So suppose you want to, from here you want to go to capital Hill. So if it is operational, then you will take a step like that. You want to go to Campus Drive, then you go till State Street and then take a right, you go to Capitol Hill. But for the operation or the declarative one, you just say that I want to go to west and then north. Okay? So that's the difference. You are not specifying how you want to do that. You just want to say that what you want at the last. So that's declarative. And what is operational? That you also specify that what you want to do that, how you want to do that. Okay? So that's the difference between the relational algebra and the tuple calculus. And so when we do, so mostly in the databases, why we learn relational algebra? It is because that at first we have the SQL language, then we transfer that into tuple calculus, or in the same way it can be changed to relational algebra, and then whatever the results that we get, means the expression that we get over here from the relational algebra, we try to make a query plan out of that and see what is the optimal procedure to get the result, and then we run or execute and then we get the result. So this is actually the procedure. So when we say that these two, this one and this one are the same because they give us the same relational instance at the last, we say that these are the two relational equivalents. So this expression and that expression, both of them are same, and that makes us something called relational equivalence. And all the query optimization comes after that. So when we get two expressions or many expressions that are equal or they output the same kind of thing, then we try to find out which one of the expression is actually optimal. So I can say I want to go to Capitol Hill and I went farther south. I went to 100 south and then I take a right turn to 700 or the State Street and then again came to the Capitol Hill. So that's a long way, right? This is not optimal. So similarly, we can have many different options of expressing this expression. So this is not a complex one, but for the complex one, we can have many instances of such expression. We have to find out which one is the most optimal. But in the domain of expressing that what is the most optimal expression, means we have to find out what is the most optimal expression, we might end up taking more time to find out that which one is the most optimal. So what we do is that we try to find out which one will give us the optimal expression, but we don't want to find out the most optimal because it might be more time complexity to find out which one is the most optimal. So what we do is that we try to find out something that is optimal as far as we know, and then we run that, because the time that we find, so time to find optimal plus the execution, so that is the total time. That is the total time. We want to make sure that this time is lower and also this is lower. But while trying to find out this optimal, if you take large enough time, then this one might not be valid. Say I take 10 milliseconds to find this optimal and then I run it for 1 second. Now say I try to find the most optimal and that takes me 2 seconds and then I run that one, say 50 milliseconds. Doesn't make sense, right? This one is 2.0050 total second and this one is 1.10 millisecond, right? So this is what I want to express you, that relational equivalence gives us the ample opportunity to optimize the query, and this can only be done after we express our SQL expression to a relational algebra, and then we execute that or make the plan for that. Okay. So now we'll talk about the union and the set difference. So till now what we have seen, that this selection and the projection operator. Yes.
I was just wondering, I guess, with relational equivalence, is there like an infinite number of like for given a relational algebra expression?
Yes.
Are there like an infinite or finite number of relationally equivalent other?
So you can actually do that, the number of combinations that you can have. So for your number of, so over here there are two expressions, right? You can do again that you do this projection on 3 different things, then you shorten out, you do S name and S ratings. So it is not infinite, it is still finite, but the combination will be very large. So it's like the combinatorics, right? The combination of all the operators that with that you want to achieve that expression. So for a definite expression, so if say you have an expression with plus and minus and multiplication, you can find that expression with many different. So if you do first multiplication, then you do addition. In turn way, maybe you do addition first, then you do the multiplication. So this is one of the things. You got it, right?
Okay. Yeah.
Yeah. So it's like a combination of them. So what you have to do is that you have to check what is the selectivity of that table. So Fefe will tell that maybe in the next lecture, that what is the selectivity of a particular relational table. So if your selectivity is less, then you are actually pruning more. So if you are pruning more, then your execution time will be less. So if you are pruning more data, means you are selecting only specific amount, couple of rows for a particular operation to go in the next operation. So in the next step, you have less data. So if you have less data in the next operation, then you will be faster, right? So that's the main motive, that you have to find the selectivity with less. Means you have to select less rows in the next step. Okay. So next we will talk about the union and the set difference. So till now what we have talked about is the selection and the projection. They always operate on a single table or the single relational instance, right? But union and the set difference, they can operate on multiple and more than, it's at least take two input for the two input relation or more than two input relation, right? And one of the things that we should keep in mind is that union is only possible when the two relational instances have the same schema. That means that they have the same set of fields and also the field types are of the same type, same data type. So if we check this one, they both have the same schema. They both have the same set of attributes. And now when we do the union operator, we get this result. So we have 21 over there. So 31 is the one and 58 is the one. Those two are duplicate, right? Those two are present in both S1 and S2. So what about the duplicate elimination? What are the operators that do duplicate elimination? Anyone? So we have till now talked about projection, selection and union. Out of that, which one is the one we don't need duplication, deduplication? Yeah, selection is the one that doesn't need deduplication. The reason is that it is already a relational instance, and out of that we are selecting a subset. So we are doing selection, say ratings greater than 8 and on a particular table, say S2. So S2 is already has all the values unique, all the rows that are unique, and out of that we are selecting only the ones that are greater than 8. So S2 was a set that has all the unique rows, and now out of that we are selecting a subset of S2, that is this one. Let's call it A. So A is subset of S2. So everyone can see that. So this one will also have unique rows, right? So that's the reason that we don't need deduplication on the selection operator. Now over here we need to have the deduplication, because 31 and 58, they both are present in the both the relational instances. Now let's talk about the set difference. Yeah.
So when you do the deduplication, do you
Yes.
do the, because I guess in relational algebra, does it still have a concept of a key? Like if you had, say, in S1, like 31, instead of being lover, it was, I don't know, other or something like that. Would there be two rows with their SID 31 in S1 union S2? Because they weren't exactly equivalent, but they had the same, even though they had the same key.
So you're saying that this 31, the key is same, but they have the different values over there?
Yeah, the ID was the same, but different values between S1 and S2.
So then this is not X, then you can call it X1, or that one may be X2, right?
Okay.
You got that point?
So we'd end up with two rows.
So right now don't think of this one as a primary key concept.
Okay.
So just think that this row, it has to be unique.
Okay.
This row and this row means if they are same, if they are equal, then we deduplicate.
Yeah, that's what I thought. I just was kind of confused because you have the SID underlined.
Yeah,
Okay.
it was taken from some slides.
Okay.
That's why, yeah. Okay. So you think of this one as a set. You think of this each and every row as a set, and each row as a single element in the set. So this S2 is a set with these 4 elements. You see that point?
Yeah.
Okay.
So,
Yes.
back to this, essentially the
Yes.
same question. So if SID is what makes this table unique, and you happen to have like one SID, like 31 repeated,
Yes.
but something else in the other columns, how do we get rid of the duplicate in this case?
So that is what I was saying, that
I missed it.
in this case, you have this table and forget about the primary key concept.
Okay.
Okay, so think of this S2 as a set, and in that set you have 1, 2, 3, 4 elements, and this one as a combination is a one element, and if that 31 and this 31 row, if anything is changed in them, then you don't consider them as equal.
Okay, so you keep both.
Yeah, you
But
keep
then
both
there's
at
no-
that time.
Okay. But then the SID is no more for the final result.
There's no constraint on the.
There is no constraint at that time.
So okay.
So this is the notion of the relational algebra, and what you are mixing with that is the concept of primary key.
Yeah.
So that is the constraint with the relational instance, not with the set. The set can be anything. You got anyone? Anyone has question? Okay. Now let's talk about the set difference. So what we have seen is that all the operators that we have seen till now are commutative and associative. So S1 union S2 or S2 union S1, both of them are same. The order doesn't change anything as the outcome. But for the set difference, we have the difference. Like if we draw something like this, say this is set 1, this is set 2, and the union is of course the whole set. But for the set difference, we'll have different. So S1 minus S2. So this is S1 minus S2. So that will be this part. So S1 minus S2 will be this part. Only this part, right? So let's do this one. S1 minus S2. So what are the common one over there? 31 is common and 58. So the result will be 22, right? So the result is 22. And now let's see what is S2 minus S1.
28.
Anyone? Yes?
28, 44.
28 and 44. Excellent. Yeah. Yes. So what we have seen is that set difference is not commutative and not associative, but union is commutative and associative. Okay? By the way, why we don't have the intersection as the basic operator? Anyone? So by basic operator we mean that they are the elementary ones. So like in chemistry we have 115 elements and there are 3 more elements, 180. So 115 atomic elements. Okay. And we don't include the compound elements in them because we can construct the compounds with those basic elements, right? So similarly over here, we can create this intersection operator or the division operator with the help of these basic 5 operators: the selection, projection, then the union, set difference, and Cartesian product. So these 5 are the basic relational algebra operators. So now let's talk about the cross product, and then later on we'll come out on the intersection one. So let's take an example at first. The Cartesian product is exactly with each pair, with each row for a particular instance. You combine all the other rows in the other instance. So so suppose we have a set that has x1, x2, x3, x4, and another set, say y, y1, y2, y3. The Cartesian product will be x1 with all of them, y1, y2, y3. Similarly, x2, y1, x2, y2, and so forth. This will go till x4 with the combination of x3. So how many? So for this instance, how many rows will be there?
12.
There will be 12, right? So it's 4 into 3. So for over here, there will be 6, right? Now one more thing is that we have SID on the first column and also over here, right? Over here and over here. So there is an ambiguity in the column names. Everyone can see that? Am I too fast? Okay. So over here we have another SID, over here another SID. So right now we introduce another operator, that is the renaming operator or the row operator. So let's see this one. This is the row operator. So this is the expression. This is the actual relational algebra expression that we want to have over here, which we want to rename. And we rename it to C. The relational instance that we have outputted is the C. So now we'll call this one as C. Okay? And if you see this 1 and 5, they have been renamed to SID 1 and SID 2. So how do we know that this will be the 5th one? Because in the Cartesian product, we first take all the attributes. So S1 has 4 attributes, right? The 5th one will be this SID, this one. And if we interchange that one, R1 cross S1, so this one, the 4th attribute will be SID, because this one will be at first then. Anyone has the confusion? Okay. So why do we need the rename operator? So in a complex kind of query where we do stepwise many calculations, so we have to do renaming of a particular instance so that we understand it more reasonably. Okay. Otherwise we can write long query, that will be fine. Okay, but another time we need that when we are doing self-join kind of thing, because at that time if we have to create some aliases. Otherwise, if you don't rename that, even you won't understand which one is the one you are doing Cartesian product with or you are doing the self join with. Okay. Now let's talk about the intersection. So I'll just draw X. So this is say A, this is B, and I want to find this one. With any operator set, you can use union, you can use reference. So how can I get this one? This is the intersection. Anyone who has not looked at the presentation on the slides can try. So this one is A, right? This whole thing is A. And how do we get this one? Say this one. This is A minus B, right? But I need this one. I need this one. So I have this A and I have this one. So if you just do A minus B, you can actually get the intersection, right? Similarly, on the other way, if you just do B minus A, see, you can still get it. But don't make the mistake of doing A minus B. That makes A bigger. So this doesn't make sense, right? It is a same operation, not the algebra, mathematical algebra. Okay? Yeah. So with intersection, we just first calculate this disqualifying part from A or either B for that one, and then you just remove it from this A. This is same as the division operator. I will explain that. Just take that into the mind that we want to see what are the disqualifying elements. Okay? These are the disqualifying elements for the intersection. So we find the disqualifying elements and then we subtract that or the set difference that from the ones that are disqualifying. Okay? Yeah. Whether do we need deduplication for this one? Anyone? We need deduplication or not? Yes or no? How many is for yes? We need deduplication, and how many for no? And many of them are no clue, right? Okay. So we don't need deduplication. So earlier what I have said that this is the minus operator. So it's still the subset of the one that we have. So if everything is unique in this A and you are removing some of the elements, you still get the unique elements, right? That's why we don't need deduplication. Okay. So for the intersection also, the set has to be union compatible. By union compatible, we mean that the schema should be same for both the relation, right? And this is already what we have covered. So 31 and 58 are the ones that are in both the set. Now let's come to the join operator. So we can also express this join operator with the basic operators, and let me show you some. So you can think of it in this way, that you first compute the cross product. Okay, so let's do that. So you first compute the cross product. So this was the result and the saver thing like this. Okay. Now you select the ones that have the same IDs. Let's go back to this one, the Cartesian. So this is the one with the Cartesian, right? So we want to do join with R1 and S1. And over here, this is the SID from S1 and this is the SID from R1. Okay? Now, after we do the Cartesian, we get this table. That is exactly which I have written over here, R cross X. Now we have to do selection, right? Based on what condition? That this SID and this SID should be equal, right? So, what you can say is that R dot SID is equals to S dot SID. I can just write S1 and then it will be equal. Okay? So, is that the does this is the complete syntax, or do you need anything more for the natural join? We need projection. So let me ask this one, that in the natural join, what is the output result or the output instance you want to you expect? What are the attributes? The attributes should be this one, this one, this one, this one. Eliminate this one, right? Then this one and this one. So if we have multiple number of attributes, say I want to match, say not SID, I will just do generic S1 dot B1 and R1 dot A2, S1 dot B2, R1 dot A3, S1 dot B3. So we have multiple now, okay? And okay, so the output one it will be, so everything from R1. So we'll have everything from R1, comma S1 except the one is B1, B2, B3, right? So in this case we have multiple. That's why we are eliminating B1, B2, B3, because A1, A2 and A3 are the equivalent attribute for this set, right? Got it? Then we do the projection of whatever we have. So I can just write this one over here. R1, comma S, B1, B2, B3. Okay? So this is exactly the join operator. And we express that one as like this. This is the natural join. So let me tell you that exactly this is not how we do it. We don't compute R cross R Cartesian S. Okay? That will make the table huge. Means the intermediate table as huge. We do it much more efficiently, and Fefe might cover that one later on. Okay? So now let's talk about the theta join operator. So we will keep everything same that we have seen. So let's do that R cross S, and then in the selection we have our condition. We can write it as theta or we can write it as C. So C stands for condition, that is condition join or theta join. So this can be any Boolean expression. So this has to be a Boolean expression which outputs either true or false. Okay? And then over here you don't have any sort of projection. Okay? That's the difference. over here with the theta and the natural join. If we have something like, so this one is actually S1.SID less than R1.SID. So the condition is still greater than, less than, you can have less than, equal to, okay? Even you can have not equal. That's still a valid one. But for the only special thing that we have is, we call it equijoin, where we have the condition as equal. So if this theta is having the equal condition, say any attribute r dot a1 is equals to s dot a1 and r dot a2 equal s dot a2, so all of them are equal. So this equal. Then we have this, we call it equijoin. What is the difference between equijoin and the projection? Equijoin and the natural join. Anyone? Is there any difference? Is there any difference? Yes?
It seems like this is more powerful because the natural join is on the keys. The equijoin can be on any sort of element of the tuple.
Yeah, so you have to specify what are the common attributes between them, right? Means you specify which one is the common attributes for R1 and S. So we have said that A1 and A2, and so A1 from R and A1 from S, they are equal for the common attributes. And there is another point. Yes, anyone?
Equijoin does not, or natural join will project out the common stuff, but equijoin still has both.
Excellent. Yes, that's the point. So you don't have any projection over here. See, that is not there. It's not there. So in equation, we don't project that one. But if we apply that condition that I have written over there, this part, then it's exactly equal to the equijoin and natural join. So equijoin with this condition, with this projection, it makes natural join. Okay? Okay. Now let's do this thing, the division. Let's start with the example. So the division operators are usually used for the sequence queries like for all. So if I say that who are the students that have taken all the courses in the department, and also like the sellers who have reserved all the boards. So for all like conditions, we use this division operator for all. Okay. Now say I want to divide A division by B. What can be the result? So this is the simplest one. Okay. So we have S1 with P2. We have S2 with P2. We have S3 with P2. We have also S4 with P2. So what could be the result? Okay, let me show you this one. Let me do the. Since all of them has P2 with them, we actually can get S1, S2, S3, S4. But now let's see with two attributes, P1 and P4, right? S1 has P1, P2, P3, P4. So it has P2 and P4, right? S2, it has P2, but it doesn't have P4. S3, it has P2, but it doesn't have P4. S4, it has P2 and P4 both. So we can actually cancel out S1 and S4, right? Means they are the one that has P2 and P4. So the result will be S1 and S4. S3 and S2 doesn't qualify because they doesn't have P4. I'll show you in a moment how to derive that one again. Okay, and for A divided by P3, so it has P1, P2 and P4. Only S1 is the candidate because S4 even doesn't have P1. S2 doesn't have P4 and P1. S3. S2 has P2, P1 but doesn't have P4. You see the point? Now let's define this one in tuple calculus. Okay?
Yeah, to do duplicate.
Let's see that. Okay. Okay, I'm doing this one. So in the tuple calculus division operator, so A divided by B, it should be all the x's that are, so these are the elements these are the qualifying elements. So for all y in B, we have, there exists a combination of xy in A. So this is exactly the tuple calculus expression for division. Okay. Now, what does it say? Let's take this example. B2. What are the y's? Y's are P2 and P4. Okay. So these are the y's. These are the y's. And so for these two, there must exist x and y. So what we have? We have S1, P2, S1, P4. So then this x gets qualified because both of them is present in A. You can see that, right? Both of them is present. Similarly, if you see S2, there is P2, but S2 P4, this is not there. That's the reason S2 is not qualified for this result, the outcome, right? Similarly, for S4, we have both of them. So that's why this is one x, this is another x. Now, what are the attributes that is output for this A division by B? It is exactly the attributes. So this is not the set difference operator. This is attributes not in B, right? Attributes in A but not in B. So we have S number and P number. S number comma P number. This is one set minus P number. So exactly the result is S number. So if you have multiple, say I have a table with A1, A2, A3, and then I want to divide it with A3, I'll get the result as A1 and A2. So this one divided by this one, I'll get the attribute as A1 and A2. Okay? So this is the tuple calculus division, but I will express how we can do that with relational algebra. So let's do this B2 and A divided by B. This one only. Okay? So just like I have said in the previous one for the intersection, we want to find the disqualifying elements, right? So over here also we would like to find out the disqualifying elements. But how we will do that is, at first let's select all the x's that are the possible result. So the possible results are S1, S2, S3 and S4, right? This is from the first attribute, S number, right? They are the possible elements. So let's project that. So let's project, let's say x, and then we project this, it's called, let's call it A, okay? So this is exactly this. Now we do the Cartesian product. We want to find out all the combination of this S1, S2, S3, S4 with the one that we are dividing. So what will be the result? S1 with P2, S1 with P4, S2 with P2, S2 with P4, P2, P4, P2, P4. Okay? This is the all combination that we can have. But in the real world, we don't have, in the real instance also, we don't have all the combination. Right? So what we do? We find out the ones that are not there. Right? So if we do like this, what will be the result? We have, let me draw it. So we can cancel out this one, it's present there, right? So it is cancel out, S1 P2 is there, S1 P4 it's also there. We can cancel out, S2 P2 is there, yes it's there. You got it, right? This one minus this one, and S2 P4 it's not there, so it will still be valid over here, right? This row is still there. S3 P2 it's there, S3 P4 it's not there, so it will be here. S4 P4 it is not there, it is not there. You got it? So only two rows. So this result is S2 P4, S3 P4. Right? Now let's do the projection. Only x. So what we get? After we do this projection, we get this part. S2 and S3. So these are the disqualifying elements. You see that? You see that S3 and S2 are not the result in this one. So at last what we need to do? We just do this projection of x with A minus this part. Let's call this as D, or the disqualifying elements, D. And this is exactly the result. So, disqualifying elements. Did you see that? Anyone who could not understand this one? I can explain again, yeah, if anyone does not understand. Does this make sense? Okay, I am live. Someone is writing, still taking the notes. Yeah, exactly here. It's there in the slides also. So at first, we do the partition product of what are the elements, all the elements with that. Now we subtract the ones from the real ones from them, then project out the one that are the disqualifying elements. Now we subtract the disqualifying elements. So the idea is to find out the disqualifying elements, not directly find out what are the qualifying elements. Okay? Okay, now we'll start with some exercises or the examples of the relational algebra. So find the names of sailors who have reserved boat 103. So from here you can see that boat and the sailors. Boats, reserve and sailors, they are the three relational instances we have, right? And we have to find out the sailors who have reserved boat 103. So that's why what we did reserve with sailors, the natural join with reserves and sailors, and we selected the boat with ID 103. Then we projected the names. Is there any alternative to do that?
Yeah.
Can you do it really efficient? Is there an efficient query? So instead of doing the join, the whole natural join, can I do something better? Yes?
You could select the reserves for boat ID 103 and then
Okay.
from that join sailors.
Yes. So by that, so if you see over here, results has two columns, but in reality, this table will be much larger, right? Much longer. So when you do the natural join with results and sailor, it might be that the intermediate result, this result and the natural join sailor is pretty big. So let's prune the 103 at first. Let's do that. Let's do this thing. Let's prune this 103 at first. Let's select that row and then do the join. Then we project the sailor name. Okay? So find names of sailors who have reserved a red boat. Sorry. Yeah. Who has reserved a red boat. So how to do that? Anyone? Yes?
First of all, join reserves with boats, so that way you have the color available. And then you can select out just those which have color red, and then you finally project out the sailors.
Okay. Yeah, that's a valid
It's
one.
not very efficient, but
That's the valid one, yeah. That's not efficient but the valid one. Because you did the join with reserve at the boards, right? But you didn't select the ones that are only the red.
yeah.
You can actually do that. You can first select the red one, right? So that's why I said that the selectivity matters then. So you are actually pruning the most of the table if you are doing the selection at first. It is not valid for all the time, but it is more often valid. Okay? So let's see the result. Did you see that? We can actually do the color red at first, and then do it with the sailor. The result. Yes.
I think too, for both this one and the previous one, you can make it more efficient by projecting out on that reserves, also projecting out the SID and the boat ID.
Is
Because they
that?
could, yeah.
Actually, I was going to be going to that point here. So what we did over here, instead of taking whole thing, we just need the SID over there. So we eliminate the columns that we don't need. So we just select the modes, then we select, did the natural join with reserve, then we only selected the SIDs. Then with these SIDs, we do the natural join with the sellers. Sellers only needs the SIDs, right? It doesn't need all the other information. Anyone have doubt? This is on the, okay. Sellers who have reserved a red or a green board. So same, instead of just doing the red, you can just do red or green, right? So this is still a Boolean expression, right? This one is still a Boolean expression. It's either red or green. Now what about the AND one? Can you do this one? Is this one valid? So let me just. So instead of doing this OR, can you just turn it into AND, and that will work? Will that work? Why? You want to say why?
Okay, yeah, because you're going to end up with the color red or green. It's just going to be the null set basically. Because
yeah, so
none
if
of
we
them
just
have two
do
colors.
color red and color green, is there a board that is with color red and green?
No.
No, right? So what do we need to do? Anyone? Let's select the first, the red ones, and then select the green ones, then do the union. Is that okay? First select the red ones, then select the green ones, and then do the union. Okay? Yeah.
So I think I missed why we couldn't do, why that it's not valid to have an OR in that Boolean expression.
Or is valid.
It is valid?
Yeah.
Okay.
Yeah. Why AND is not valid?
It's-
I said why AND is not
Yeah,
valid.
I caught
for
that, yeah.
Yeah.
Okay.
So when you change this statement, the question from OR to AND.
Oh, I see. Okay.
Okay?
Okay.
Then we can't do that.
Okay.
Exactly?
Yeah, I'm with you now. Sorry.
Yeah. Oh, sorry, yeah, that is the intersection. Yeah. It's AND. So the sellers who has reserved the red board and also the green boards. See now this row came into the renaming operator. Otherwise it will be a bit clumsy, right? If you write both of them over here, that's why you just have that named red and green. Okay. Find the names of sellers who have reserved all boards. So this all came into place. Now, anyone? Means what is the operator that we should look into?
The division?
The division operator. Whenever this for all comes, it's most often that you should use the division operator. If this is also a tricky question, then you might have to, you might not be able to use division operator. But most often, for all case, we have this powerful division operator. Okay, now for this one, let me see how can we do this one. Yeah. So is it just this board and So it's, what is the question? We need the
I think it was sailors who reserved all boats.
sailors who have reserved. Okay. Yeah, sailors. So sailors who reserved all boats. Now we should start with what? We should divide sailors with boats or something, or what?
I think
Anyone?
we should join sailors and reserves.
We should join
Yeah.
sailors with.
Reserves.
Okay, but that is the later point. Yeah.
Okay.
Anyone? Yeah.
First, you need to project on reserves and boats so that you can use the division operator. So, like for reserves, you have to get rid of day and just have SID and boat ID,
Yes.
since day is not in the table.
Exactly. So, but what is the most important thing over here is that we have to do the projection. Yeah, this one. So if you see that this part, this projection of BIDs of the boards. Okay, if you don't do that, what is the? I still have the just 2 and 4. So this board, you will have this B name, color, and all these things, right? So in the division operator, if you just divide with BID, B name, and color, with anything that doesn't have this B name and color. So suppose you are dividing this reserve, right? And reserve has SID, BID, and date, right? So when you divide this one with these 3 things, automatically the result will be null, because B name and color is not there. So at first you need to cancel out these 2. You need to project only the BIDs from both. Then you get what? You get 102, 101, 102, 103, 104. Right? And now when you do the division, can you do simply this reserve divided by boards? So reserve divided by boards, SID, BID, and day. So it actually says, if you do this one, it actually says that who has reserved all the boards in a particular day. Right? So if anyone has reserved all the boards in the same day, then that result will be there. So that is too restrictive. We just want this part. Projection of SID and BID. Now the result will be this SID. Right? The attribute that will only be in the schema is this SID. Anyone who missed this one? So this part is very important, this part and this part. You have to project only the ones that you care for. So over here, you care for only SID, BID. Because you are dividing it with BID. Now BID is gone, you are left only with SID. Okay? And for getting the names, you can just do the join with this SID. That is temp SID, temp SID join with sailors, you can just get the name. That's only for getting the name. But you already get the SID at least. Right? Now to find sailors who have reserved all interlink rows.
Just do a selection.
You do the selection beforehand. While so this projection BID, you only get the ones that are named interlinked. So you just change that part. Okay? Make sure you read this one very well at home, because Fefe is gonna give some questions with this division, I'm pretty sure. Okay? Okay, for each board, find the sailors with smallest sailor ID who has reserved this board. I think I'll leave this to for the homeworks. Yeah. Similarly, for each board, find the sailor with the largest rating who has reserved this board. So you need to find the largest rating. Okay? There comes the set difference operator. You find the ones that doesn't have the largest rating, that is always below the highest rating. Those are the ones with the SR, and then you remove those SRs. You get only the result with the highest rating. Okay? So, in summary, what are the basic operators? It's selection, projection, union, then cross product, and set difference. Okay? And there is also another operator, that is renaming operator. And we can define many compound operators. The most common ones are the intersection, division, and join. Yes?
So how would you do, I guess without the renaming operator, do stuff like self-joins?
Yeah, I said that. For renaming operator means...
I mean, if you didn't use the renaming operator, like, because I guess...
You can use the braces, right? You can use the braces and say that this is the first expression, then you do join with the second expression again with the braces or the parentheses. We can do that.
Okay.
Yeah? But it is harder to do with the SQL. Because there you need the aliases, right? They won't allow you to do that. So that's the difference between the relational algebra and the SQL. So from SQL we derive the relational algebra, but relational algebra is done at the last level. Means this is for doing the query optimization. Okay. When you are more involved into the databases, you are into the database engine. You have to do the query optimization. You have to learn this. Okay? Okay, so I'll start with the SQL. We still have 10 minutes left. So I'll just start with the queries. Oh. Okay. So SQL stands for Structured Query Language. Why we came with the Structured Query Language is because there are many kinds of databases. Each one has their own copyrights. Each one has their, but there needs to be a standard so that we people can actually query, or we people can understand what we want to get from the databases, right? You can say, yeah, I know MySQL. The other guy says that I know PostgreSQL. The other can say that I know some columnar storage, maybe Vertica, HP Vertica or something. So if every one of them has different kind of query language, then you're in trouble. You have to learn each and every one, right? So they come up with a standard that they has to maintain for the query languages. So earlier there was ANSI, and then so they don't often change this thing very often. So the last one that we have is the standard SQL 2011 that MySQL, PostgreSQL, and other databases use. So, but apart from that, they do have some uniqueness in their query type. So they have, suppose you want to see underlying system table or something, they have different system tables. MySQL has different, PostgreSQL has different. The way to describe the table is different from MySQL and PostgreSQL. You do /d plus in PostgreSQL. You write describe or DESC table name for the MySQL. So these are the different things that they have still different in them. Okay. Let's start with the create table. I think I'll just finish this slide and then we'll wrap up. Okay. So let's see how this is exactly taken from the documentation of MySQL or 2011 MySQL standard. So create table, these words that is written in capital, they are the keywords. Means these are the reserved keywords that you can't use as a table name or the column name or something like that. So these are the reserved keywords that create table. Okay. Then this table name, you can specify your table name. That is there in the smaller format, small letter format, small alphabetical letter. Then there comes this first bracket of the parenthesis, where you specify all the column names, column constraint, and the table constraint. See that column constraint, they are optional, and they are actually given in the third bracket of the braces, this part. So they are optional. Whatever that comes with that type of braces, they are optional. But we need at least one column name for a particular table. So that's why we have a column name, and we have to specify the data type. The data type can be character. You can specify with char in MySQL, or varchar as the variable length character over there. You can specify what type of integer or the numeric values it can have. So these are all the numeric ones. Then you can specify it is as date or timestamp, and also as a serial or the unique ID. Now you need to specify one column at least and the data type. Then comes this default expression. What this means is that you can express a default value for that column. If you don't specify while inserting your data, you can specify that while creating a table, that if you don't specify that value while inserting, it will take that default value. It can be default as a null, it can be default as a 0, that you can specify while creating the table. Okay? And there are some column constraints that we'll talk about in the next slide later on, maybe next day. And these column constraints are like this column value should be in range. So you have something like check this value. So age can't be maybe not more than 150. Okay, say 0 to 150. You can't have 4 digits number over there. So you need to have a check of kind of thing over there for that column. So you can specify that column constraint over there while creating the table. And table constraint, you can specify like references to a foreign table. If you have done the undergrad course, you know that there is the primary key foreign key relationship, so that there is relationship between another table with this table that you are creating. You can specify the referential integrity through this table constraint. Also, you can say that this is my primary key. Combination of 2 columns can be a primary key. You have to specify that one in the table constraint. Okay. So anything that is in the to brace, that is optional. Other than that, everything you should have to specify. Okay? We'll continue from detail in the next class on Thursday. Okay. Thank you so much.